Hello everyone, welcome to the second week. And this week we're going to learn about section 6.2, which is about finding out volume of a curve after rotation, and also section 6.3, which is about finding density, mass, and center of mass. So this video will concern section 6.2 only. Well, the first thing that I would like you to note before you start this lecture, for any such sections, I'm sorry, for any such problem that concerns finding volume and blah blah blah, problem that concerns. Or area under the curve, make sure that you are drawing a picture, which I did not see in your first assignment. I will send a separate announcement saying that what is missing from the assignment, but seeing from the couple of submission in your assignment, I saw that many of you have not drawn any diagram at all. This is not acceptable in the case of exams or like future assignments. So whenever you are attacking a problem that involves, some graph sketching, you have to do it. And you will be given some point based on that. The pictures might not be up to scale, that's fine. Like, I don't really expect you to like draw everything up to scale, but some illustration should be there. With that, let's go into the section. So in this section, there are essentially two parts. So also, we will not cover section 6.2 for 2.4. We will, which is kind of easy, but like just to like make you guys less confused about the material, I'm skipping this. So there are two part of this, chapter, which is this. So say you have a function. Just a moment. Okay. So now with this function, you can do two things. Let me rescale it. Yeah. So with this function, you can do two things. Number one, you can rotate the function around x-axis, right? So if I do so, what shall I get? I shall get something like this, right? And say I'm like doing it in the interval a to b. So if I do so, I shall get a conical, like a circular kind of thing, kind of like a cylinder, right? Mm, Okay, it is not up to scale, of course, but something like this, right? You kind of reflect the function across x-axis and you kind of get a conical section. And you get an object, right? This is the object. So this is rotation with respect to x-axis, right? And if I do rotation with respect to y-axis, this is slightly better to draw. So this is rotation with respect to y-axis, right? So I take a graph, I rotate it with respect to x-axis, I get a solid object. I rotate it with respect to y-axis, I get another solid object. Now the question is, what are the volumes of this thing? So 6.2.2 will tell you about the volume of this. And then 6.2.3 will tell you the volume of this. That's it. So let's jump into it. And let me just do an example. Actually, let me just first state the theory and then we'll do an example. So the first theory, so let me do for rotation with respect to x-axis first. And the first elementary theory that we'll need for this is this one, which I'm like copying from the textbook. The disk method. So if I give you a function Rx between an interval AB, after a revolution, what you get, I mean, the object you get has the volume, this one, right? So let's see an example. So I'm doing example 6.2.4. So actually it's example 6.2.2, my bad. So y equals to 4 minus x squared, right? So this is our Rx. Find the volume. Find volume of the object obtained by rotation around x-axis. So how do you do it? So let's see. First step, draw a picture. Let me just check if it is recording. Wait a minute. Yeah. So draw a picture. Okay, for this you need some idea how to draw a graph of arbitrary function. So what does the graph of 4 minus x squared looks like? So, oh, okay, I forgot to tell you the interval. So Yeah, so the interval is like where it cuts the x-axis, kind of implicit here. So first of all, yeah, perfect. So notice that I haven't said what interval I'm going to use. So whenever that is the case, always remember that the interval would be between those 2 points where the graph cuts x-axis. Meaning you have to find what these 2 points are, because these are the 2 points where the graph cuts the x-axis, right? So find out the points where y cuts the x-axis. How would you do that? Well, if if I mean, okay, find out, like, solve this equation y(x) equals to 0. Solve this to get the x coordinate of the intersection points. Right? So, and how would you do that? In this case, y(x) is 4 minus x squared. So solve this equation. This means x squared is 4. This means x equals to plus minus 2. Right? And why solving y(x) equals to 0 would give you the x coordinate? Because see that at this 2 point, the y coordinate is actually 0, right? So that is why I was saying that, okay, let us find out for what value of x the y of x is 0. Anyway, so my point is this point is negative 2 comma 0 and this point is 2 comma 0. Right? And then you are trying to rotate this guy around x-axis. So what you would get is something like this. Mm. Some volume, some solid like this, right? Something like a football, right? Then what is the volume? Use this method. The volume is, use this x coordinate that you have just found, negative 2 to 2, then pi rx squared dx, but rx is simply 4 minus x squared. So this is pi 4 minus x squared dx. Okay, I'm not doing this integral for you, but if you calculate this guy, what you will get is 512 over 15 pi. Okay, any question? Oh, sorry, this should be. Just make sure that how you know how to calculate this integral. You have to expand this guy. So meaning that 4 minus x squared whole squared is 16. Okay, let me just write it. So 4 minus x squared whole squared is 16 minus 8x squared plus x power 4. Once you have this, now I think you should be able to integrate this very easily. using the very basic integral formulas. So I would ask you to like stop here and have a look at this and digest this thing, and then solve some of the some of the activities, right? Any question? I mean, okay, it's kind of pointless to ask questions. Um, so boring to teach online. Anyway, okay, I assume you understood. Then let's go to the next problem, which is about, I mean, the next theory, which is about the disk method. No, the washer method. I don't know why they found these names. So let me first show you the theory. So in the previous method, that is the disk method, there was just one function. But if you think carefully, we are actually, I mean, there are actually two functions, right? One is Rx, right? Which is in this case 4 minus x squared. And the other one is this x-axis, which is nothing but y equals to 0, right? So essentially, what you are doing, you are considering the region that is created by intersection of these two curves and then rotating that around x-axis. Make sure you wrap your head around this, what I'm trying to say here. So if you look at this region, right? This is the region we have rotated around x-axis, right? And how did you get this rotated? How did you get this region? You first of all consider the intersection points of the curve 4 minus x squared with the x-axis, which is nothing but y equals to 0, right? The function y equals to 0. And then you got the region, right? And then you rotate it. So I mean, this next theory is a generalized version of the previous setup. So instead of x-axis, now I'm saying that, okay, I give you two functions, y equals to capital Rx and y equals to small rx. So previously this capital Rx was y equals to 0, like Rx was 0. This Rx in the previous question are 0, right? Did you mark? If Rx is 0, you get disk method. So meaning that this washer method is a generalized version of the disk method, right? So my point is that now if I have two different functions, and if I try to, you know, if I try to find the intersected region and rotate it around x-axis, what shall I get? So let me show you an example and then we'll go and then you will like see the theory in action. Okay. Note that this is very similar to that what we have seen in the previous theory, right? In the disk method. It is just difference of capital R and small r square and then the same integration as before, right? So y equals to 4 minus x squared. So this is going to be our, yeah, small r, actually capital R, and y equals to, I think, x squared. Oh no, x plus 2. And this is going to be a small r. So our task is to find out the volume of the object created by rotating the the intersected area between these two curves around x-axis. right? So this is example, I guess, 6.2.4, in case you were wondering. So first of all, you have to find out the intersected region, right? So again, let me just copy paste the and then also let us try to write down the function y equals to x plus 2, right? And what would that look like? See, okay, let me first draw the picture and then I will describe. Actually, it can be better. So this is the line y equals to x plus 2. Okay. You will see why I drew the line through negative 2 comma 0. Okay, first of all, find the point of intersection of R and R. How do you do that? Well, again, equate and solve it to get the x coordinate of the intersection points, right? So how do you do that? So it is 4 minus x squared equals to x plus 2. Solve it. So that means x squared plus x minus 2 is 0. That means x plus 2 times x minus 1 is 0. That means x is negative 2 comma 1. So if x is negative 2, Rx equals to Rx is 0. And if x is 1, then Rx equals to Rx equals to 4 minus 1 square, which is 3. Also note that this is equal to 2 plus. Okay, let me just do it separately. Rx equals to 4 minus 1. And also note that. Right? What I wanted to show you here that, okay, this for this negative 2 comma 1, sorry, for this negative, for x equals to negative 2 and x equals to 1, you really get the intersection, right? Because you can see for x equals to negative 2 and x equals to 1, the y coordinate matches, right? When x is equal to negative 2, both rx and rx are 0. And when x equals to 1, both capital Rx and small rx are 3. So I really did get the point of intersection, right? Meaning, let me just try to show it on picture. As you can see that the first point of intersection is this, negative 2 comma 0. And the second, oh man, the second point of intersection is this, which is 1 comma 3. right? So let me make a note. Negative 2 comma 0 and 1 comma 3, right? And what are you doing? You are just trying to evaluate so let me try to copy this thing. So this is the region of intersection between these two curves, right? And now you are going to rotate it around x-axis. So try to understand what kind of object you will get. It will be a hollow object, right? Because this is the region that you are rotating. Let me see if I can get. I'm sorry. This is the region you are trying to rotate, right? So what you will get is something like this. Perfect. And then an object that looks like this. Mm, right. Yeah, I agree. This is not a good picture, but well, this is the best I can do when I draw by hand. So this is the kind of object you will get. And what is the volume of this object? Well, that's not too difficult to find out. Volume is equal to. Remember, you have to figure out which function is greater, capital R or small r. So you have to figure out which one is bigger, 4 minus x squared or x plus 2. But as you can see, in this region, this is 4 minus x squared and this is x plus 2. So 4 minus x squared is definitely bigger than x plus 2, right? So no problem. So this is find out the x-axis for the intersection point, negative 2 and 1 by rx squared minus rx squared. So that is why drawing picture is so important, because you need to understand which function is bigger, capital R or small r. If you do it, you will get negative 2 to 1 by 4 minus x squared whole squared minus x plus 2 whole squared. I'm certainly not doing the integral. It is up to you. Sorry. If you do it, you should get 108 over 5 pi. Okay. So that's all about rotation around x-axis. Now, let's jump to 6.2.3. Rotation about y-axis. And what is the theory? Absolutely similar to that of rotation of x-axis. Just replace x with y. So in the case of x-axis rotation, you need the function y equals to something 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 in x. For example, y equals to 4 minus x squared, or y equals to x plus 2, or y equals to e power x, and whatsoever. But when it comes to y-axis rotation, you need the function in terms of x. So you should get x equals to y squared, or x equals to y cube, or x equals to y plus 2, and so on. And then use the exact same theory as for x-axis. So let me do example 6.2.6. Just express all the functions as x equal to ry, x equal to small ry, if ry is more than equal to ry, then the theory is exactly same as in 6.2.2, meaning the integral would be a comma b pi ry squared minus small ry squared dy. And yeah, where a and b are the point of intersection, x coordinate of the point of intersection of these two functions. So let's see an example and make everything clear. So the functions are, let me see, y equals to square root x, and y equals to x power 4, right? Now see, these functions are not as we want it, right? We want something like x equals to something in y, but here it is y equals to something in x. So how should we do it? Well, you know, we can certainly do something like this. So y equals to square root x, meaning x equals to y squared. Perfect. And y equals to x power 4 means x equals to square root, or maybe I should write like this. Right? Also find out the point of intersection. Find out the y coordinate of the point of intersection. So previously we were finding out x coordinate of the point of intersection, and now we want to find out the y coordinate of the point of intersection, right? And how would you do so? Well, just equate. So this is say, so equate ry equals to x equals to small ry, right? And solve it as before, exactly as before, right? So y 1 power 4 is y squared. Solve it. So that means y equals to y power 8, right? So this means y times y power 7 minus 1 is 0. That means y is either 0 or y is either 1, right? So these are the y coordinates for the point of intersection. Also, don't forget to draw a graph of these things, right? So remember what y equals to x power 4 looks like. These are something like this. This is y equals to x power 4. And what about y equals to square root x? Well, if you know that the graph of y equals to square root x looks like this. Makes sense? So these are the point of intersection, right? So I think this is 0, 0, and this is 1, 1, right? And you are rotating this guy around the x-axis, right? Okay. Again, this is some sort of a hollow cap. Anyway, you don't really actually need the figure other than to find out which function is bigger. Now see, rotate your perspective, right? Okay, it doesn't really work. I mean, my screen is rotating here, but try to see the function from y-axis, right? If you do that, which function is bigger? This is y equals to x power 4. And you can see that this blue line is bigger, right? If you see from the y-axis, right? So that means the volume is pi x power 4 squared, right? Minus, sorry. Y, yeah, I'm sorry. This should be, okay, my bad. This should be y squared. So this is y equals to square root x, which is same as x equal to y squared. My bad. I made a typo. So this is going to be y squared minus y1 power 4 squared dy. Right? Make sense? And what is this? This is like integration 0 to 1 pi y power 4 minus square root y dy. I leave it to you to do the integration. What you should get is 7 over 15 pi. Any question? So that's it. That's all you need to know about function for x-axis, okay? Of rotation around y-axis. Exact similar theory. If you, let me see if I can do one more problem. Okay, let us do 6.2.3 part D. So y equals to 2x and y equals to x cube. Again, what is the area? So this is 6.2.2 activity. For one more example. So find the region, find the volume of the object created by rotating around y-axis. So what should you do? Well, so first function is x equals to half y. The second function is x equals to y power 1 over 3, right? And then find out the intersection point. So half y equals to y power 1/3. That means y equals to 2 y power 1/3. If you want, you can cube everything out. So y cube equals to 8y. That means y times y squared minus 8 is 0. That means y is either 0. Actually, let us find out the intersection point in a different way. See, whether you see this function as a function of y or function of x, the intersection points won't really change, right? Like if you draw the graph, things will be much more clear. So the graph of y, my bad. This is what y equals to x cube looks like, right? And what about 2x? 2x would look something like this, right? Let me use a separate color. Right? So this is the point of intersection for these two functions, right? Now see, the point of intersection won't change whether you want to view it as function of y or function of x, right? So, meaning what I want to say is the following. So find out intersection point, right? And how do you do it? Well, you can either equate in terms of function of x, that is also fine, or you can equate in terms of y. So just to bring some diversity here, I'm going to equate as function of y and find the x coordinate, and then I'll find the y coordinate. So x cube equals to 2x. That means x times x squared minus 2 is 0. That means x is 0 or square root 2 or negative square root 2, right? Now you can see that for the intersection, the x coordinate is always positive here, right? So this x coordinate is unnecessary, meaning that this function would also, oh, actually, maybe I'm wrong. Maybe you actually need this intersection point as well. Yeah. There are 3 intersection points, as you can see, right? So this intersection point is for x equals to 0, this one for x equals to negative root 2, and this one for x equals to positive root 2, right? And now you are rotating this entire thing around x-axis. So what you will get is a cup, right? So disregard my comment about the disregarding negative root 2. Anyway, our task is to find out the y coordinate. Now, since these are intersection point, y equals to x cube, right? That means, y equals to 0 cube, which is 0, square root 2 cube, which is 2 square root 2, and negative square root 2 cube, which is negative 2 square root 2, right? So you have to integrate from negative 2 square root 2 to positive 2 square root 2, right? So in other words, as you can see, yeah, this is kind of tricky. So this is, yeah, so this is going to be 0 to square root 2. Okay, for 0 to 2 square root 2, this part or this part, notice that the x cube function is larger, right? So x cube should come first and then 2x, right? I'm my bad, my bad. I'm really sorry. We are doing is function of y. So we should do something like this. That means x is half y and x is y 1/3, right? So Notice that this blue function is for x equals to y 1/3, right? So this should come first, minus half y squared dy plus negative 2 square root 2 to 0. For negative 2 square root to 0, that means this part, notice that this function is larger, right? Because now we are on the negative side of the x-axis. So what you will have to do, actually it doesn't really matter. Okay. Yeah, because this part will clearly have more. Yeah, never mind. We don't have to do this thing. I was being extra cautious. So simply, you don't need all this. So just simply go from 2 square root 2 to here, pi y power 1/3 squared minus half y squared. Because you can clearly see that the function that is here has always more area than the line 2x, right? So yeah, you don't have to worry about that. So this thing is always going to be positive. So that's my point. Okay. So find this out. I'm not going to do this integral today. Okay. Just use the standard integral formula. So that's it. That's all about section 6.2 and 6.3. So let me just do a quick summary. So the most important formula is this. No matter what you are doing, whether you are like rotating around x-axis or y-axis, the theory remains same. Just figure out which function is bigger, capital Rx or small rx, right? In this example, 4 minus x squared is bigger. In this example, when you try to find out the function in terms of y, x equals to y power 1/3 is bigger, right? From the perspective of y-axis. And then just use the formula of Gaussian. That's it. Okay. So that would be all. I will be posting the homework very soon as well. Okay. Sounds good. See you.